All right. Welcome everyone to another episode of the F Word, programming in Fortran. Today we're going to be talking about how to build a nonlinear shallow water solver. Give me a second here. There we go. We're going to be building a nonlinear shallow water solver with the Spectral element library in Fortran. I have posted links to notes down below in the description of this video. Feel free to request some access to that in case you want to follow along. If you do have questions you want to ask during the live stream, simply hit subscribe to our channel so you can get access to the chat window. So let's just go ahead and get started. So first off, of course, we need to acknowledge our references for today. So a lot of what I'm going to be talking about is going to be building off of work that's already been done, particularly the top two books. First one from Randall Levesque on numerical methods for conservation laws. So I'm pulling a good deal of information about the Riemann solvers that we'll be using for shallow water equations. And then David Kopriva's book on implementing spectral methods for partial differential equations, of course for a lot of the discretization. So if you tuned in 2 weeks ago, some of these do look familiar. The two papers on the bottom. It's particularly setting the direction for where we're going, which is building stable methods for solving shallow water equations. So where we're going to start today is on a little bit of a derivation of the shallow water equations, and we'll cast everything in terms of a conservation law, take a look at the discretization, and talk about how we're going to actually implement this in Self. And in the latter half of today, we'll get into the code, do some implementation, and start doing some test runs. So the shallow water equations, they are in some sense a subset of Navier-Stokes. Particularly if you're looking at really thin fluids with a very small aspect ratio, so the depth to the lateral length scale that you're looking at tends to be very small. And in general, in that case, what we actually have is the hydrostatic primitive equations, which are shown down below. You have the basically what we're modeling is the two components of velocity, u and v. In a lot of cases in geophysics, we cast things in what's called an F-plane, so the coordinate system you're working in will be rotating. So we have a Coriolis force, we have advection of momentum, and then we have pressure gradient forces. And in this form, we're really neglecting the effects of viscosity because the length scales are fairly large, so you'll see no dissipation terms on the right-hand side. And the cool thing about hydrostatic primitives is when you're in these really thin aspect ratios, the advection of momentum in the vertical momentum equation kind of goes away, and what we're left with is really what's called hydrostatic balance. So the pressure can be determined if you know what the density field looks like. And the density field here is just represented by rho prime. We have the acceleration of gravity, and since these are really built off the Boussinesq equation, so we don't have sound waves in this problem, we basically measure the density as if it were just an anomaly off of a reference background density rho naught. And the other equation here is what we call the continuity equation. Now originally this is a mass conservation equation, which under the Boussinesq approximation gets rid of dynamical changes in the density that are usually caused by compression or rarefaction of a fluid. In this case we've filtered those out, and so we're going to start here just to show you where the shallow water equations come from. And then once we get those, we'll go ahead and dive into the conservative form. So in this diagram, what we're looking at is just a two-dimensional slice of a fluid where we have some bottom topography down below at z equals minus h. And the free surface is allowed to move up and down with location and over time. And that top surface is given by z equals eta. So the total fluid thickness here that we're actually working with, I'm going to denote by the letter capital H. It's going to be eta up to the free surface and then down to that fluid bottom. And what we can do with the hydrostatic primitive equations, if we assume that the density anomaly is 0, so we look at what's called a barotropic fluid, in other words, there's no buoyancy acceleration going on, the right-hand side of that hydrostatic balance goes away and the pressure ends up being constant with depth. And the pressure that we work with is just rho naught times the acceleration of gravity times that free surface height. So I can change the pressure in the fluid by lifting the free surface or depressing it. And when you have that, where you have a pressure that's independent of depth, so on the right-hand side of the momentum equation, you have a function that's independent of z. And what that allows us to reasonably assume is that the velocity field itself is also independent of z. So we actually drop out the vertical advection of momentum terms, and we're just left with the momentum equation. I'll just do the zonal momentum equation. It's just du dt, u du dx, plus v du dy. We'll ignore Coriolis here just for the sake of doing this derivation, and we'll bring it back in later. And on the right-hand side, what we end up with is minus g deta dx. Okay. And to arrive at the shallow water equations, what we really want to do is vertically integrate this equation so we get an expression that tells us what the fluid transport looks like. So if you were to integrate from minus h down to the bottom topography up to the free surface, of course with all these terms being depth independent, since they don't depend on z, what we can actually do is just simply move all these terms outside of the integral and multiply by eta plus h. So we'll do this on both sides of the equation. So I'm just going to very quickly cheat here and remove that integral. And what we end up with is h, capital H, which is our total fluid thickness, is going to be equivalent to minus g, capital H, deta dx. So if I do the same thing for the meridional momentum equation, what I'm left with is capital H dv dt, u dv dx, plus v dv dy equals minus g capital H deta dy. So for now, we're going to hold off on doing anything more with the momentum equations because we need to take care of this continuity equation down below. Whoops, I did not mean to delete that. So the continuity equation where what we had was du dx plus dv dy plus dw dz. Basically what we need to impose are boundary conditions for that vertical velocity in order to work out some of the details on what continuity equation becomes. Because essentially what this tells us is that volume is conserved, and so we need to express this in terms of this shallow water setting. And the way we're going to do that is first, if we just like we did the momentum equations, we're going to integrate from top to bottom. So we have from minus h to eta du dx plus dv dy dz. I'm going to separate the u and v components from the vertical velocity. So we have minus h to eta dw dz dz. That's all got to equal 0. Okay. Now on this first term here, again, u and v, we're assuming are depth independent because of the reasons we stated earlier. So what we get out front here again is just h du dx plus dv dy plus, now I'm integrating a derivative with respect to z, so what I get is w at the free surface, so the vertical velocity at the free surface, minus w at the bottom. Okay? Now, what we want to impose for the boundary condition here, in this case, is no normal flow, essentially. Now on the bottom, that's fairly straightforward to do. What we want to really have is that the total velocity field, and I'm going to go ahead and just move up to the top here. The total velocity field, so u multiplied by the normal to the boundary, so if I were to draw a normal vector down there on that bottom topography, that normal vector is really given by the gradient in the topography plus 1 in the z direction. So no normal flow, what that means, let me back up one step here, is that the total velocity field dotted with the boundary normal has got to be 0. And when you're on the bottom here, what that equates to is dh dx, x hat, dh dy, y hat, and 1 in the z hat. It's at least parallel to that normal, so we can go ahead and use that. Now the u field, of course, is u in the x direction, v in the y direction, w in the z direction. So when we write all this out, what we get is u hx plus v hy plus w has got to be 0. And we can move things to the other side of the equation to solve for w, because this is the condition we want to impose on the bottom topography. So you get minus u hx plus v hy. Cool so far? Now at the free surface, we have to deal with the fact that things are moving. So essentially, it almost turns out to be the same kind of condition we impose, But this is always a weird statement, at least I found it weird when I first learned it, is we basically want to say if there's a particle that's on the free surface, it's going to stay on that free surface. And so in other words, the distance of a particle where it sits is not going to change over time. If it's at the free surface, it's going to stay there. And the way we express that is the material derivative of z with respect to time has got to be 0. Sorry, z minus eta. So the distance between that particle position at eta has got to be 0. So the derivative, the material derivative of z minus eta is 0 at z equals eta. It's kind of a weird statement, but what it ends up allowing us to write, so one, the material derivative of z, so the material derivative of the vertical position is just the vertical velocity. And I got minus d eta dt material derivative is 0. And eta only depends on x, y, z, and t. So I can manipulate things a little bit here, basically move that d eta dt to the right-hand side. And I've got my boundary condition for the vertical velocity at the free surface. All right, so now we've got these two statements. We can actually plug those in back into our continuity equation down below. And again, as Jesse puts it, I'm going to use a little chalkboard magic here. W at eta becomes d eta dt. Okay, and technically, right, since h does not have a time derivative, I can equivalently write this as the derivative of minus h, or I can just say derivative of h dt, and I change that sign to a plus. Okay, now of course, doing a little more chalkboard magic, we know that capital H, this big H, the total fluid thickness is just eta plus h. Again, we'll do a little more chalkboard magic, and we've got dh dt there. And that's all equal to 0. All right, so almost there. We got a couple more things, because what we want to do is actually cast this in what's called conservative form. So I'm going to write out these terms here, and then we'll go back, we'll pull back up those momentum equations and do some simplification there so that we can ultimately write this in conservation form. Okay, so dh dt, the material derivative, is the partial derivative of capital H with respect to time, not little h, plus the velocity, so u dh dx plus v dh dy. And again, since these don't depend on z, I don't have any contributions in the vertical direction. Okay, and then I also have in the so what I have in the continuity equation is dh dt plus h, and then convergence of the lateral components of the velocity field is 0. So if I substitute these in, I get again local derivative of h with respect to time plus u capital Hx plus Vhy plus h ux plus Vy is 0. We can actually, use chain rule here to combine UHX and HUX into just the total derivative of UHX, and we can do the same thing in the y direction. Okay, so that's the form of the continuity equation that we're going to be working with. Basically, it says that the total volume of a fluid column, of a column of fluid, is going to be preserved from place to place. So that's one statement. Now let's pull back up what we had for our momentum equation. So if you remember, before I erased it, we had h du dt plus u ux plus v uy. I'll go ahead and throw in those Coriolis terms here. Not much harm done by having them. So we have gh d eta dx. And then again, that meridional equation, we have dv dt u vx, and now we're advecting the meridional component, vvy plus f times u equals minus gh d eta dy. And the cool thing here is I can actually use this, whoops, that's not what I wanted to do. I can use this identity, the volume conservation identity, to actually bring the h inside of the material derivatives in the momentum equation. And what this allows me to do is write the momentum equations as hu derivative with respect to time plus hu squared derivative with respect to x plus HVU with respect to y. We'll keep the Coriolis term separate because it is. And then on the right-hand side, we've got minus GH dA to dx. And then for that meridional equation, I'm going to drop it down below because I'm running out of space. Or you know what? Do more of that chalkboard magic. There we go. Make some space up top. We get something similar for that meridional equation. So HUV x plus HV squared y minus plus FHU is minus G big H dA to dy. So we're almost there. Now, of course, this is certainly one form you can start from. Now, if you've done numerical methods before, and you really have to be careful about which equations you start with, because discretely you're not always guaranteed that the discrete form is going to have properties like a chain rule or an integration by parts. And in fact, if your numerical discretization is not exact, you can have problems where, like, if I have a flat bottom topography, what you really want to have is certain cancellations in the terms so that a quiescent fluid stays quiescent. So we'll talk more about this in a minute, but I'm going to just do one more step here to finalize these equations, because in its current form, the problem with the current form of the equations is if I were to discretize from here, what I end up having is a flux function that only depends on the advective component, and it completely misses the gravity waves. Gravity waves are going to come in from these pressure terms on the right-hand side. So if I start from this form, I don't have a whole lot of time to derive all this stuff, but essentially we don't satisfy a particular criteria called the Lax-Friedrich theorem. The Lax-Friedrich theorem basically says that if I can conserve each of these quantities, HV, HU, and H, then I can say that my numerical method is going to have the appropriate speeds for shocks in my problem should they develop, which we should expect shocks to develop for nonlinear systems like the shallow water equations. And so the way we recast these equations is by doing a basically chain rule on this right-hand side and bringing those pressure terms into the conservative flux. And so at least in that case, when we do the discretization, we can show later that we actually get satisfaction of the Lax-Friedrich theorem, and we can at least guarantee that we'll get the shocks and gravity waves that will propagate at the correct speed. So that's what we're going to do next, is we're going to just do a little chain rule action on this right-hand side to bring the pressure term into the conservative flux so we can have that property. But unfortunately, the point of today is to show you another problem that this brings up that we'll be addressing in 2 weeks. All right, so that right-hand side, the way we want to bring that pressure term in, essentially what we can do is on the right-hand side, so I'll just do it for the zonal momentum equation, and the same argument applies for the meridional. So I've got G, H, eta y, and we know that big H is just the bottom topography plus eta. So that must mean that eta is just the full fluid depth minus the bottom topography. Nothing really fancy going on there quite yet. So we got minus G capital H, and we got a big H inside of there minus the bottom topography derivative with respect to y. Okay. So now what we can do is on the right-hand side, I've got G H squared on 2y, again using our a little bit of chain rule here. And then what I'm left with is plus G big H little h derivative with respect to y. And so on the right-hand side, I basically have gradients in the bottom topography is what I want to leave over there, and it's this term that I want to bring over into my conservative flux. And again, we'll do some chalkboard magic. Hail the chalkboard magic. Thank you, Avis. What we have on the right-hand side is G capital H little h with respect to y. And then in the y derivative for the what I'll actually do, let's do this in red. This y derivative, what it becomes is hv squared plus gh squared on 2 with respect to y. And then down in the x component, we get something similar So it's the x derivative for the x component where we're going to change that one. It's going to be hu squared plus g h squared on 2 with respect to x. And then on the right-hand side, that sign becomes g big H dH dx. This is the form we're going to start with, and this is what people classically call the conservative form of the shallow water equations. And we call it conservative form at least because the numerical methods themselves, in most cases, and at least the ones we're going to be developing today, they're going to conserve these quantities, HV, HU, and H, both locally and globally. So they'll satisfy the Lax-Wendroff theorem when we get shocks and gravity waves that propagate at the right speeds. So now what I'm going to go ahead and do from this point is we're going to take this equation and just cast it in terms of that conservative form that we've been working with. So if you remember from the last few weeks, what I've been trying to do with self is always have problems cast as a time derivative of a vector of prognostic variables plus the divergence of a conservative flux. And then we have some additional source terms on the right-hand side that we'll call Q. So the underbars here really indicate that it's a vector of prognostic variables or a vector over the variable space, and then the arrow over top, like what you see here on the flux vector, means it's a physical vector. In other words, it has x and y components representative of physical space. So the solution vector here, this S, is going to be the volume flux terms. I'm not sure what happened there. So we have HU, HV, and then we've got the fluid thickness. Okay, so those are the conservative variables we're going to track in the code. These are going to be the things that we're going to model, so we can, eventually we'll pull out things like velocity and vorticity and all these other terms, but there's various ways we need to go about calculating those. Now the flux term, so remember the flux, if we go back here, we've got basically a combination of advection and pressure, right? So what we're going to do here for those guys, so the flux vector, so let's start with HU. It's going to be HU squared plus GH squared on 2 in the x hat direction. And then we've got a v hat direction. So now we've got, oops, what's going on here? Did I lose my pencil? I think I might have. Give me a second. There we go. H, U, V in the y hat. And then for the v hat for the meridional component, we'll have H, U, V in the x hat plus HV squared plus GH squared on 2 in the y hat direction. And then for the fluid thickness, all we have is that advective flux for the fluid thickness. So if I were to really write it out, full component form, HUX plus HV in the y hat. All right. So there's a couple nuances with this. Oh right, let's do the source term here, and then I'll get back to that point. So the source term here, we have a Coriolis. So again, I'll go back one slide just to refresh your memory. We've got Coriolis term, which I'm going to put on the right-hand side. So for the U term, we'll actually have positive FHV. For the V equation, we'll have negative FHU, and then we've got these bottom gradient terms. Okay. So hopefully I didn't already forget what I just said. So we have FHV positive plus G big H little h with respect to x. For the U equation, we've got minus FHU plus G big H little h with respect to y, and then assuming that there's no sources or sinks of volume in the fluid, we'll set that to 0. So that's step one in self. Every time what we're going to do is we're going to basically specify, if you remember, we have a source term that we need to specify. We need to specify the flux, and then we need to handle the Riemann solver, which we'll talk about here in the next slide. So already we've defined the few things that we need to do in order to create the solver in self. So we've got these two terms. There's a little bit of a nuance here because really what we track in the code is going to be H times U and H times V. So if I want to calculate U or V, I really have to formulate a rational function. in order to get the velocity component. So when I actually go to calculate h times u squared, what I have to do in the code is calculate hu squared and divide by the fluid thickness. And this is a little bit of a problem when we do the numerical method, because the numerical method, if you remember, what we do is we approximate each of our variables as polynomials of degree n. And if my actual solution is not a polynomial of degree n, or the actual function I'm approximating is not a polynomial, then I incur an error. And specifically when I calculate, that is hu squared. So when I calculate something like hu squared, I will end up with an error, because what I'm really approximating is a rational function of polynomials, where in the numerator I have a polynomial, in the denominator I have one as well. So there's one source of error already, because our flux function is actually nonlinear. There's a few other errors we're going to touch on here in the next couple slides, but keep this in mind. The other reason I bring this up is because what we did to get to this form of the equations is we assumed that we could apply a chain rule. And I alluded to it a little bit earlier that, well, at least when we go to the discrete form, having the property of a chain rule be preserved depends on the idea that you have no error in your approximations. And unfortunately for this set of equations, in particular this term, when we moved in the pressure term here, I now will end up with something that has an error in its representation. So when if I were to put in a quiescent fluid with like a flat free surface height and no initial velocity, if I have variations in the bottom topography, this term here in the flux, when I compute the divergence of the flux, it's not going to exactly balance with the source term on the right-hand side if I have varying bottom topography, and it'll actually lead to spurious flows. So I'm going to purposefully do that today to motivate what we're going to do in 2 weeks, which is basically starting from what's called a split form of the equations, which is a weighted average of the conservative form and the invective form to effectively cancel out that error. But for today, this is a good place to start, because we'll get most of the bits in place to do a shallow water solver, and then we'll kind of course correct here in the next couple weeks. There are a couple more things we need to talk about. So I already mentioned one of the errors we're going to incur. So essentially, to go from that continuous form, it's ds dt plus divergence of f is equal to q. What we do is, and I'll just do a simple domain here. So if I had, I don't know, like a donut for my domain, so this is a solid wall here, what I'm going to do is divide that domain into quadrilateral elements. So I got 4 nodes and 4 sidewalls for each element. And within each element, we're going to approximate HV, HU, and the fluid thickness, H, as polynomials. And not only that, we're going to solve the weak form of this equation. So if you've done the weak form, essentially we arrive at that by multiplying the equation by a test function and integrating over a volume. And so if we do this for each term, so we got dv. On the right-hand side, we've got q with a test function dv. This may look a little weird at first if you haven't done these kinds of method, but what this allows us to do is I can do essentially integration by parts on this divergence term, so I can move the requirement of smoothness off of the flux function and put it onto the test functions. And so that's the first step here for casting this in terms of the weak form. So let's go ahead and do that. So we get a boundary integral of f dot n hat phi. I'll call that ds, so it's a boundary of v. This will be over v. And then we've got minus the internal terms, so we've got f dot grad phi dv, and on the right-hand side we still have q phi dv. Now the next step, usually what we say is that the test functions we're looking at and the solutions, we expect them to basically be what are called square integrable functions. So over my domain, if I were to square my solutions and my test functions and integrate over that entire space, I'd get a constant number. That's a pretty easy constraint for a lot of functions we care about to meet. The The deal is in the discretization is we restrict our attention to a subset of that space. We don't look at all possible functions. Instead, for our discretization, we look at a set of polynomials that are basically of some known degree, right? So we restrict our attention to a finite dimensional space. Rather than all possible functions, we say polynomials of degree n. So that's the first assumption, is phi is in polynomials of degree n. Then the next assumption we make is that the solution is basically polynomials of degree n. So the solution vector itself is a vector of polynomials of degree n. The other assumption we make, and this is the big one here because it's the root cause of a lot of our aliasing errors, is the flux that we have is also in that space. So even if I say my solution is in polynomials of degree n, as I showed in the previous slide, right? If I'm calculating as part of my flux a rational function, I'm incurring an error, okay? And then on top of that, there's going to be an additional error in how we approximate these integrals. So that's the part of the coming up with the discrete form is making these assumptions that we're going to restrict our attention from all possible functions to polynomials degree n. And specifically what we do is write, for example, I'll do just one of these. Let's say s is the function we care about. We're going to write it as a sum in two directions, so I and j. So it's a tensor product of polynomials in one direction with polynomials in another. We have the nodal values of the function that we're going to treat as our degrees of freedom, and then we have Lagrange interpolating polynomials in each direction. So LIC, LJ, let's say C2, so C1 and C2 for our two different directions. And when we first started the series, I did put out a few bits of notes. Particularly, there's a Google Collaboratory, which you can find in the Open Collective link down in the description of this video, that walks through all the steps to come up with what we call the quadrature. So here, essentially, if you have Lagrange interpolating polynomials, let's just do 1D here. What we need to do is decide on where in an interval, let's say from -1 to 1, we place the interpolation points or the interpolation knots. And there's some pretty clever choices out there that guarantee what's called spectral accuracy. So what that really means is that the error you're incurring only depends on the smoothness of the underlying function. And for functions that have infinitely many derivatives, in other words, they're complete, you enjoy exponential decay in the error. So that's what we do, is we choose these points. What they're called are the Legendre-Gauss points. At least that's what I prefer to use in self. We also have the Chebyshev-Gauss, Chebyshev-Gauss-Lobato, and then there's Legendre-Gauss-Lobato as well that are available. So essentially, within each element, we have a grid that is defined by the Legendre-Gauss points inside of that element, and we calculate the nodal value. We have the nodal values of the function at those points that we track. So if I have polynomials for my solution, if I plug those in for the flux, I get rational functions in the flux, so I incur an error. The hitch here is that the test functions as well, we replace with each of the Lagrange interpolating polynomials. And essentially what this gives us is for each element, if we're in 2D, we're going to get n+1 squared equations for n+1 unknowns. And it turns out that the mass matrix, so the matrix that multiplies this first term where the time derivative is a diagonal matrix. So it's really easy to invert. That's what I have shown up here in so many words, or so many mathematical characters up top. Essentially, we're going to map this element to a reference computational space, make all these approximations, and I have basically the Jacobian of the mapping multiplied by the vector of solution variables. And let's see here, so this term, so where we're doing f.grad test function, that becomes basically a matrix vector product that we can do to calculate the internal contribution to a derivative. And then these boundary terms, the trick here is we actually replace this with an approximate Riemann flux. And so the reason why we need to do that, and actually let me change colors here. So I might have this blue element, for example, neighboring that white element that I've already got there. And this element over here is going to have its own representation of the solution. And this element over here is going to have its own representation. And somewhere along this edge, we're going to have to communicate momentum and volume exchanges. And the problem is, as I have two different states, this element's going to tell me it's going to be one value, and the element on the other side might have a different value for the solution. The Riemann problem is essentially a problem that's set up to solve exactly this. And so what we do is basically construct, if you remember from last week when we did the linear solver, we sorted out the vorticity wave, which didn't move in the linear equations, and the two gravity waves that go two different directions, and basically did upwinding to create a Riemann flux. We're going to do the same kind of thing with the nonlinear equations, except we have to do an approximate Riemann solver. It's incredibly expensive to do them exactly. And without going into a full derivation, this is where I'd say Randall Levesque's book is absolutely fantastic for covering a lot of this material. What we're going to be working with today is what's called the local Lax-Friedrich's Riemann solver for handling those fluxes between elements, and they also work for the boundary conditions. So this is the local Lax-Friedrich's Riemann solver. And again, the problem here is so here's my element boundary. I've got a bunch of nodal points where I have estimates of the solution from either side. So I have what I'll call the solution on the left. I have the solution on the right. And the normal vector is going to point from the left state to the right state in this setup. And so in the code, the way this works in Self is you're always thinking about where you're at in the context of this primary element on the left side. And we can compute what those exchanges need to be. So here I've got n hat. I think I've got everything specified I need to. So when I calculate the Riemann flux, so f dot n hat, so that flux on the boundary, which depends on the solution states on the left and right side. For local Lax-Friedrichs, we get 1/2 of the fluxes from either side. Oops, not f star. So that's going to be the actual flux evaluation. So f dot n hat with the left state plus f dot n hat with the right state. Okay, and then we're going to subtract off. There's some parameter here, which I'm going to define in a minute, alpha times the jump in the solution. So SR minus SL. Okay. Now for local Lax-Friedrichs, alpha is going to be the maximum of the eigenvalues of our flux Jacobian matrix, which I'll walk you through how to define that if you missed last week. The flux Jacobian matrix using either the left state or the right state. So when you're doing these Riemann solvers, what you'll often find that in the end, really what you need to know are the eigenvalues for your flux Jacobian matrix, and certainly that's the case for the local Lax-Friedrichs Riemann solver. In most linear methods out there, approximate Riemann solvers, this is what you need to know. So let's just quickly go over again how we come up with those eigenvalues, again in case you missed it last week. What we need to do, so one, we need to know what f dot n hat is, and then what we're going to be looking at is calculating, like I said, the flux Jacobian matrix, which is really the derivative of that flux function with respect to each of the solution variables. So for this problem, what it will be is the derivative of the, I'm just going to use f for f dot n hat. We're going to do the HU flux with respect to HU, the derivative of the HU flux with respect to HV, and the derivative of the HU flux with respect to H. Now the next row, we're going to do the derivative of the HV flux with respect to HU, derivative of the HV flux with respect to HV, and the derivative of the HV flux with respect to H. And the last row, derivative of the H flux with respect to HU, right? And you can see the pattern to build this matrix. Okay. In the notes that I've provided, in the link below, which you'll find at the Open Collective page, I've got a lot of this worked out for the linear equations. I'm working on finishing up the full nonlinear equations, but they're getting there. Now what we want to do, essentially what this allows us to do, if you think about the advective form of the problem, so essentially what we need to do is reconstruct the characteristics of the system so we know how to do upwinding. This is where all this stuff is rooted in. Essentially what we're after is, if you think about the advective form, let me go back one step just to show you where this comes from. So we've got dsdt plus divergence of vector f is 0 if I ignore those source terms. In the advective form, essentially what we can write is the basically dsdt plus the flux Jacobian matrix dotted with grad s is 0. And you know, with shallow water, we've got 3 equations that are fully coupled. And essentially what we want to do is decouple these equations by diagonalizing that matrix. In other words, we want to find its eigenvalues and eigenvectors so we know what directions waves are going, and then we can choose the appropriate solution for upwinding the value. So if I find waves that go from left to right, I want to be using SL to plug in for the flux, and if I'm finding waves that go from right to left, go the other way around. Now, of course, with nonlinear problems, you also have other solutions that can come in here. You have shocks and rarefaction waves, and there are special ways you need to handle that. And essentially what ends up happening when you do these the local Lax-Friedrich method is this additional term here is really set up to provide a necessary amount of dissipation, so we get what's called the entropy stable solution. It's a whole lot of theory. Again, I encourage you to check out that book from Randall Levesque. It's got a lot of the details that explain this stuff. So what I'm going to skip past and just share with you is what these eigenvalues are for shallow water equations. If you want to check out last week's video, I have the derivation for the linear eigenvalues, in which we found 2 gravity waves that go, basically the eigenvalues were plus and minus root gh, so the gravity wave speed. And then the third one was the vorticity wave that had no velocity. Now for the nonlinear systems, what we have is we have the first pair of eigenvalues is the normal velocity plus root gh. So we have a gravity wave now that's moving with the velocity field. We have a gravity wave moving against the velocity field. And then we have a vorticity wave that moves with the velocity. Right? Vorticity is just advected around. So we got 0, 1, and 2. So off the bat, already calculating the maximum of these eigenvalues, we can actually go ahead and cross out this bottom one, because un plus or minus root gh is always going to be bigger. And so essentially what we're going to do to put in the local Lax-Friedrich's Riemann solver is calculate the normal velocity plus root gh, normal velocity minus root gh, using both the left state and the right state, get the maximum out of those 4 possible values, and plug that in for alpha on the right-hand side. We know what the flux function is because we defined it already in the previous slide, and that'll be that. So just to recap what we got, right? So we've got the shallow water system. We've defined it in terms of conservative form, so we're going to be tracking the total fluid column momentum, so h times u, h times v, and the fluid thickness. We've got our flux function down below, and then we've got our source terms, which has Coriolis integrated into it, and we've got variable topography. So what we're going to do next is go ahead and hop into the code, and we're going to go ahead and program these up. And basically, I'm going to do two examples here, one with the flat bottom and a quiescent fluid, to show you that we can get a quiescent fluid. That'll be our first test to make sure this code is actually doing something reasonable. And then what I'm going to do is put in a variable bottom topography and a quiescent initial condition, and show you we get spurious flows that develop from that. And then we'll pick back up in 2 weeks to talk about how to get rid of that error. So let's go ahead and jump over to the laptop, and we'll go ahead and get started. All right. So I see we got a comment in here. Is this part of some event? I just stumbled. I'm glad you came here from Reddit. This is actually just something I like to do every other Friday, so I'm glad you're able to join us. Thanks for tuning in. All right, I'm actually going to go ahead and hop out to another system here, because we're going to start easy. All right. So again, if you've worked with before, or if you've been following these videos, essentially everything is defined for us on the bottom end in terms of giving us access to polynomials and various derivative operations, and we're going to basically build on top of this particular model class. Since the last time I did one of these, the model class has changed a little bit. I found a few bugs in the calculate tendency, but just to refresh everyone's memory, essentially if you're developing your own model using self, so if you want to program in Fortran and run on multi-GPU platforms to do conservation law solvers, everything is built from your perspective or from the developer's perspective on top of this abstract class called a model. And the model has a lot of procedures that are defined for you, so you don't have to write your own time integrators. So far we've got the first order forward Euler and Runge-Kutta third order Williamson's low storage third order Runge-Kutta. So as I start to develop more time integrators, you take advantage of all these things that are predefined for you. There's a few things that end up being deferred in the end for you to define. So built on top of this model, we actually have I've started to concretize things for models in 1D and 2D, and soon I'll be getting into the 3D stuff here. But essentially what we want to track for a model, right, is we have a solution, and when we get to doing diffusive fluxes, you'll need to have solution gradients to hang on to, so you can do diffusive fluxes should you want to have those. Typically we have velocities, and then of course the other things that I mentioned before, we have flux, source. Eventually we calculate a flux divergence in order to calculate a tendency for the solution. Now each one of these models is also associated with a mesh, which I'll show you how to define here in a minute, and some of that internal geometry. So inside of each of those elements, we actually do coordinate transformations to a reference element and keep track of all the metric terms so that you can do calculus operations in map geometries. So self is meant to provide you all those tools so you don't have to think about it, and you can just focus on programming up your conservation law solver. The routines you end up needing to define for your particular method are the source term, the flux, the Riemann solver, and then if you really want to get into doing like variable boundary conditions, things like that, you can do that. There's also file IO routines that are built in for you. So the workhorse of this class, again, that's already predefined, is this what we call the calculate tendency. So let me go to the one for the model 2D. So the calculate tendency essentially runs through a sequence of steps to implement a discontinuous Galerkin spectral element method. It takes care of a lot of stuff for you. The main things, again, you need to define are source, Riemann solver, flux method, and if you have special boundary conditions you want to do, you can put those in, doing a procedure override in Fortran. So last time we met, I did the linear shallow water equations, which if you're following this project on GitHub, which is again, the link to the self GitHub repo is down in the description. What we did last time is essentially define a linear shallow water model. We did a type extension of the model 2D class. We added a Coriolis parameter. Gravity and a fixed fluid thickness. So today we're actually going to make this variable. We're also going to do some more complicated things like have the nonlinear flux method, etc. So we're basically, the idea, at least my approach to programming a lot of these things is defined models or example models in the code that's already there to build off of to give you a good starting point. Chances are is if it's gotten into the develop branch, it's fairly stable. Not perfectly stable until it hits main branch, but it's usually a good place to start. And certainly if you were to reach out on the GitHub issue tracker, I'm happy to help you along. Okay, so what we're going to do is actually take the linear shallow water solver, we're going to copy it for our nonlinear solver and kind of modify it from there. So of course, let's make sure I'm on the right branch. Yep, and I did go ahead and create a new branch for today. So what we're going to do is copy the linear shallow water to, I guess we'll just call it self shallow water, not support routines. That'll be good. Now with each of the Fortran programs that are there, if you're doing GPU acceleration, there is a subdirectory for HIP. So HIP is an API from AMD for doing portable GPU programming. So you can write basically what looks like CUDA kernels that can be compiled to run on both AMD and NVIDIA GPUs. We're actually going to do that today. So I'm also going to go into that HIP subdirectory and copy the linear shallow water, and we'll call it shallow water, just to match its Fortran counterpart. All right. So our job today is really to edit both of those to do the nonlinear solver. Okay, so let's start by first adding a few terms that we need here. So what we want to do is we want to make fluid thickness variable. So we can have fluid, or the bottom topography essentially, variable bottom topography. Okay, so if I have variable bottom topography, I'm also going to want to have a bottom topography gradient. So I'm going to need to add those two things there. So let's go check the model class. So self also, I basically provide a suite of objects for scalars, vectors, and tensors in 1D, 2D, 3D that have a memory layout that has seemed to work pretty well for performance on both CPU and GPU hardware. So it's a nice balance depending on what hardware you have available. And those are encapsulated in these like what I call mapped data types. So you'll see, like, for example, in 1D, I've got these map scalars, 1D, 2D, 3D. We've got vectors as well. So what we're going to do is we're going to need a mapped scalar in 2D for the fluid thickness, and then we're going to want a mapped vector for the gradient of that. So we're going to go ahead and just steal one of these declarations. So I'm going to do a map scalar for the fluid thickness. Okay. And then we're going to do a mapped vector in 2D for the sorry, I keep calling it fluid thickness because in the linear solvers, essentially this is the fluid thickness, and the free surface height is just the first order expansion term, and it doesn't affect the fluid thickness. It's almost like a passive term. Anywho, so we'll say bottom topography for this guy here, and then we've got fluid, we got the bottom topography gradient. So that's a big change from the, so this is meters over meters, I suppose. All right, so that's one big change so far. Eventually we'll do variable Coriolis parameters, so you can do beta planes or things that are far more complex if you have variable background vorticity. So first thing I suppose I should do is just get rid of linear in just about every word here. So just to make sure I'm only catching linear shallow water, we'll just replace that with shallow water. Okay, cool. So that's done there. And all I've got to do now is, because I add these additional parameters, it's usually a good idea to add an override for the initializer. If you're developing a solver, like if you remember when I was doing the advection solver, I didn't really add anything new to the extended class, and so you could actually just take advantage of the built-in initializer for the model class. But since again we're adding these additional parameters, it's kind of necessary that we override our own initializer. So let's go ahead and take care of that. So the initializer, what you need to have, what's required to come in is the number of variables, which we're actually going to go ahead and hard set to 3 for HU, HV, and the total fluid thickness. And then we actually have Fortran targets, which are like pointers. They have an address. They basically store an address in memory rather than the actual stuff stored in memory, so that externally when we write the main program, you can create your own mesh, your own geometry, your own domain decomposition if you're using MPI, which is also a nice built-in feature of Self. You get MPI and GPUs for free. So we'll pass those in. You can basically use pretty much everything that's here. For the default, we're going to change out H because we want to change how that's declared. And we're just going to copy some of these initializers for each of those components. So here we'll have H and H grad. And that should be good there. So I've already provided, so the cool thing here is actually, so each variable in the mapped data class and even in the data class underneath the hood has associated metadata with it. So you can actually label your data. So you can give it a name, you can give it units, and you can give it a description. So what we actually have here is the volume flux. So it's meters squared per second. And it's x component of the volume flux. And then here I've got HV. So we'll go ahead and set that. And we got volume flux. All right, and then here it's not eta anymore, it's actually going to be H. And we've got the total fluid thickness for this one. All right, so what this allows us to do is actually when you take advantage of the file IO routines, this will automatically populate the headers in the tech plot output with the appropriate variable names, the appropriate number of variables. So again, you don't have to worry about all the other bells and whistles of having to do stuff in Fortran. It's already provided for you in this library. Now the cool thing is it turns out that we can use the same boundary condition specification almost as we did before. What we need to do is I guess this may be premature to get rid of the the constant fluid thickness, but I'm gonna go ahead and actually bring that back. What we want to do is specify basically radiation and no normal flow boundary conditions. And the radiation, the way the boundary conditions are set is, so remember on each edge we're doing a Riemann problem, so all we have to really do is set the external state. So what I need for a quiescent state is to know what the background topography is. So actually what I might do is just make that variable so we know what a quiescent state looks like. Actually, no, I actually have that in H. That's fine. Actually, that's fine. Yeah, we can use that in H because H is going to hold our bottom topography. That'll be good. So yeah, so volume flux, you're absolutely right. It should be meters cubed per second, but we're looking at volume flux. I need to think about this one while I'm coding here to figure out how to phrase this appropriately. But essentially, you're looking at an infinitely thin fluid column that we're tracking h times u, which if you were to do an integral of that quantity over a line, you would get meters cubed per second. So you're right. Yeah, I guess it's more like a volume flux per unit length. Thanks for pointing that out. Okay, so what we want to do for the radiation boundary conditions is essentially set a quiescent state for the fluid. So again, if you haven't coded in Self before, there are particular do loop patterns that you'll see over and over and over, and so far I've been sticking to them and they've been pretty good in terms of getting ideal performance. But essentially we loop over elements, we loop over the sides of the elements, and then we loop over the quadrature points on each edge. And then we're basically going to set what the external state should be. So for a quiescent fluid, we have no velocity. So the first two terms, u and v, or hu and hv, are going to be 0. And then the background thickness, what we want to actually do is set this to, so we have the object, this, which is your shallow water object. The attribute underneath that is h that we want. And then what we want is the boundary term for h, which is going to be indexed over the quadrature point. Then it's going to be indexed over the variable, which for h, there's only one variable. So we're going to do 1. And then we have I side IL. Okay. Whoops. What I need to remember is underneath, so the way the map data class works is you have interior points, so those internal quadrature points to an element. You have boundary points for your quadrature element, so you can index over the edges. You also have this ext boundary, so it's a way to impose an external boundary condition or an external state that you want to use. But underneath each of those, you have host data for things that are stored on the CPU, and you have device data for things that are stored on the GPU. So what we need here is the host data. You'll see when we talk about how to do the GPU wrapper here, you see I'm passing this device data pointer. So we'll talk about that in a minute. Okay, so that's radiation, essentially a quiescent state. So we basically, the fluid thickness is the background fluid thickness, so just from the topography with no free surface height and then no velocity. The cool thing is for the no normal flow condition, we can actually reuse the linear conditions. Essentially what we're saying here is that we have no normal flow, so no normal flow, the tangential component of the velocity field is held constant, so between the internal and external state, and then the pressure is held constant between the internal and external state. So that's, it turns out when you work this out for the prognostic variables we have, HU, HV, and H, it looks almost identical to what we did before. So we can actually leave that alone, and then we'll fix our default boundary condition, which will default to radiation in case someone doesn't provide a boundary condition flag. So it'll just get energy out of our system, which is a stable thing to do. So that's the boundary condition. So let's do the source term next. We're going to do the CPU side, and then once we finish defining the CPU side, we'll do the GPU side. Okay, so here when we're doing the source term, we're not doing things over edges, we're doing things internal to the elements. And the loop pattern for that is to loop over the quadrature points in 2 dimensions. So you have I and j going from 0 to the interpolance polynomial degree. And then we're going to loop over the elements. And then we can just set the source term. So I've already got the Coriolis term in here. What we need to add is the bottom gradients here. So let me go ahead and just do a line continuation so this looks a little cleaner. All right, so if you remember, what we need to have is G times the fluid thickness. So we have solution interior, host data again, because we're right now working on the CPU side, IJ. So the indexing pattern here for interior points is the quadrature points first, then the variable. So here for the variable, what I need is the total fluid thickness, that's the third fluid variable, and then the element. And then I need to multiply by the bottom gradient, which we're going to have to set up a routine to calculate that bottom gradient. So we'll do that here in a minute. So we got this percent H grad interior host data I J1 IL. And this actually reminds me I need to go back into that initializer and make sure that the number of variables for H and H grad is set to 1. So we'll take care of that in a minute. So let's copy these last 2 lines and then slightly modify it. Oh, right, H grad is a vector. So the leading dimension on a vector is actually the vector component. So here we're getting the x hat component for that vector. Okay. Now, what I want to do is go ahead and put in a line continuation here to clean that up, and then we'll copy those 2 lines and slightly modify it so that we get our y derivative in the bottom topography. So we got h grad, and now we got 2. So that's pretty much it there. And then again, the source term for the volume is 0, or for the fluid thickness is 0. Okay, last we got the flux term. So last time we did the linear shallow water equations, it was just G times the free surface height. It was really nice and easy. This time we've got something a little bit more complicated. Let me pull those back up from the notes. So what we need to have for the U, so this is no longer U velocity, this is now HU. This is the flux for HV. So I var is 1 is HU, I var is 2 is HV, and the free surface height now is total fluid thickness. All right, cool. So what we have in the x direction is, I'll just put it in the comments up here. So we have HU squared plus GH squared on 2 in the x hat direction. And the y hat direction we have HUV, right? What I'm considering doing is, if you remember let's see, if I go back into that model class, there is this velocity thing I can take advantage of. And in the, let's see, calculate tendency, let's go to that. In the calculate tendency, I think there's a step we can leverage to just go ahead and calculate the velocity as that rational function. So I'll do like hu over h will get me the u velocity, hv over v, or sorry, hv over h will get me the v velocity. What I can actually do is override this PreTendency method to calculate, to fill in the velocity field. And once I have the velocity field, I can use that down here in the flux method later in the process. So I think that's what I'm going to do. So if I go back into shallow water, what I'm going to essentially do, all right, let's do this first one. So we got this times velocity interior host data. Okay, I've got 1 for the x component of that velocity, ij. Again, the velocity actually only has one variable component every single time, so that's okay there. And we've got il for the element index. So we've got u, and now we need to multiply that by the solution. So I'll do solution, which is a scalar, so we can get rid of this guy here. So now I've got, so this is u, and this is hu, so multiplying together I get hu squared. So we're looking good so far. I'm going to add to that g times the fluid thickness squared, all on 2. So what I'll do here is do 0.5. Now in Fortran, when you're doing precision, if you're using constants, if you have it, so throughout self, we actually have, and I'll actually show you where it's defined. In the constants class, we can control the precision using a C preprocessing flag. So if you, when you build the code, if you define the double precision C preprocessing flag, it'll set this press to real 64, so you get 64-bit arithmetic. Floating point arithmetic, and then it'll set C press, which is used for our integration with the HIP kernels, to a C double. Otherwise, it's going to default to single. So when you see press running around on these constants, essentially I'm just trying to be verbose and tell the compiler that this half better be 1/2 in double precision. Okay, so I've got what I need is gh squared on 2. So I've got my divided by 2, I've got my g, and essentially I can square this. This is just a habit. I'm sure you could just do the double asterisk and 2 for squared, but I'm just going to fall on my habits just because I've always done it. We'll just multiply by the height again, so no big deal. Okay, so that's hu squared plus gh squared on 2. So now let's do hu times v. So we can actually just take this first half here, copy it down below, and modify it. All right, so I've got the v velocity. Whoops. Right, I've got the v velocity here, and I've got hu. All right. So we're going to basically do this for the meridional equation. So let's go ahead and copy this. Let's see what my line numbers are here. That can help. 72 up to 63, so that gives us 9 lines. And we'll go ahead and set the flux for the v equation. Okay, so I'm going to flip these around. What I need here is, so for the first one, what I really need is HUV. So, and this is where things get weird, because technically this is HUV, but so is this. If I change this to U and I change this guy to HV, that's also HUV. And so there's this ambiguity a little bit in terms of how we do this. Of course, I could do an average of the two, but you know, these are open questions in terms of how we actually do this implementation. I'm going to go ahead and start with this, with the idea that I have my thing that's setting the characteristic is going to be that rational function I calculate, and then I'm going to use my prognostic variable in that advective flux term. Now this is the x component of the flux for the HV equation, so I need to change this first one to 1. So let's go ahead and bring that up to the top just to make it nice and neat. Whoops. So we got that. And then this one down here is going to be HV squared plus GH squared on 2. Wow, I really botched that. All right, that's looking better. So here what I want is V and HV, so I'm going to use the second component. I'm going to use the second variable there. And then I've got, again, that GH squared on 2 is already there for free. So we're good. Now this last one, I just need to have HU and HV, so I can actually get rid of what I used to have was the background thickness multiplied by U and V from the linear term. And we're just going to use HU and HV for those flux components. So far, right, what we've done is we've redone the initializer. Let me go ahead and jump in there. So in the initializer, right, I did need to do this. I needed to set the number of variables for H grad to 1 and the number of variables for the fluid thickness to 1. That's good. Velocity's got 1 variable, but the solution's got a few more in there. Now, ideally, we'd also set the manual destructor for this so that we can deallocate those additional variables. I'll handle that between this video and the next one. Right, we did the initializer, we did our boundary conditions. On the CPU side, we did source, we did flux, so now let's do that Riemann solver. It's the last thing we need to do. Let me pull that up in the notes here so I know where I'm going with this. So essentially what we need to do for the Riemann solver, again, we're now looping over edges because we're doing edge fluxes between neighboring elements. Now the cool thing that the way I've set up self is in the tendency calculation. What I actually do for you is interpolate, because the Gauss points actually are not on the element edges. You need to prolong the solution to those edges. So I do that here with the boundary interp, and then I do this side exchange, and this is where all the MPI stuff happens, and we fill in basically the ext boundary attribute of the solution attribute. And this makes it actually really easy to do communications between elements, because now every element says, I know my internal state and I know what the external state is, and we can essentially loop over all the element edges and just take advantage of that. So what you'll see, remember how I said there was a left and a right state? The left state is what I'm going to be thinking of as my internal state, and the right state is the external state. So you see where I calculate UNL and UNR, that's actually where those are coming from. But here, to get those velocities, which is part of this calculation, we're actually going to go ahead and use that velocity variable. And I see already I'm going to have to do communications for the velocity. So we'll need to add that to our PreTendency calculation. So we've got velocity, boundary, external boundary. And okay, so let me go back here. So remember, the loop structure for doing things on element boundaries is loop over the elements, loop over the sides, and then loop over the quadrature points along that edge. The geometry attribute for the model gives you the normalized boundary vector that points outwards for the element. So we've got n hat. We've also got the magnitude, because basically, remember, if you do divergence theorem, you're actually doing a line integral around the element. So in the end, when we compute the flux, we'll need to multiply by the original magnitude of that boundary vector, which gives us the little unit of length we need to multiply by to actually do a proper line integral. So we'll grab that. Obviously, we need to recalculate what the gravity wave speed is, because now we have variable fluid thickness, and so the gravity wave speed will be variable from place to place, not just because of topography, but because of the solution itself. So what we're going to do is a CL and a CR. So we'll have a left state and a right state for that. And we're going to do a similar kind of thing here. So actually I can move. Oh, let's cheat a little bit. So we've got A to L, A to R. Let's do this. Okay, so if I've got the total fluid thickness, if I take the square root of that and multiply by G, that gives me the gravity wave speed from my internal state, and then I can get the gravity wave speed from the external state. All right, So that's that. Okay, so we've got the velocity on either side. We've got the gravity wave speed on the other side. I will go ahead and just grab eta. Might be duplicative, but we're going to need it just to make things nice and easy when we code up the flux below. So go ahead and get rid of that. I don't know why I deleted that first line anyways, if I was going to end up here. Oh well, we're okay. So I've got my internal states, I've got my external states, I've got the gravity wave speeds on either side. And remember, what we're doing is the Lax-Friedrich solver. So let me clear. Yeah, the linear one's actually pretty easy because we can do an exact upwind solver, which is nice. Which is, again, if you missed that last week, the video's still up there. Essentially, what we need to do is evaluate the flux function on the boundary for the left state and the right state, average those, and then subtract off the maximum eigenvalue multiplied by the jump in the solution. That's a mouthful. So let's do this. Let's do FL. So we'll do actually flux L and flux R. And what I'm going to end up with down here is, so I need to multiply by the magnitude, so I get basically the length I need for my boundary integral. What we're going to have inside here is 1/2. We'll do flux L plus flux R minus, let's do alpha, times the jump in the solution. And the solution here, oh, goodness gracious. It's good. This is going to end up looking pretty ugly to start, so that's okay. It's okay to have ugly code. Sometimes ugly code runs fast. I don't know. So let's do this. Let's do solution. We want. This is going to drive me nuts. I'm going to go ahead and do this. We're going to copy these, and we're going to do. I just like working with something that's a little bit easier to read, and then we'll worry about any optimizations that need to happen. So we'll have HUL, HUR, HVL, HVR. All right, so HV is 2 and HU is 1. Whoops. Okay. And we'll worry about declarations here in a minute. So if any of you are wondering why I haven't declared it yet, that's I'm just sketching out what I actually need, and then we'll go fill stuff in, and of course let the compiler tell me where I botched everything. So we've got HVL. It's going to be HUR minus HUL. So we got basically you're averaging the fluxes. We get the maximum eigenvalue on 2 multiplied by the jump in the solution. So we'll do the same thing here, except using. So let's do this. Line continuation, copy that, and then try to make our life a little bit easier. All right, so we got flux L, flux R minus alpha, which we're going to calculate in a minute. Then we need HVR, HVL. And then for the free surface height, again, it's going to be flux L, flux R. Oop, I need to be careful because I have a flux for each of these. So we'll calculate. This will need to be a 3-dimensional array there, and we'll need a flux for the thickness. Okay, so then we just have HR and HL. That should be good. So change this from A to L and A to R to HR and HL. All right, and then we're going to go through and calculate these flux L and flux R. So what is this? Flux L is going to be what I need is for the, let's just do it for the first one here. So for HU, remember we have HU squared plus GH squared on 2. So what I need to do is HUL times UNL, so the normal velocity on the left-hand side, plus gravity times the fluid thickness on the left side squared on 2, so multiply by 0.5. Okay, so that's for the left side. So let's do this. And again, I'm not really worrying about efficiency to start. It's just let's get something that works and functions and is legible so we know if we made a mistake. So this one is going to be, I almost forgot. So I need the x hat component of the normal vector. There we go. So I knew it didn't look right. So we need n hat 2 here. So this one's going to be HVL times the normal velocity, and then the y hat vector multiplied by the pressure component, and then we've just got HUL times n hat 1. Actually, yeah, so we'll do that. N hat 1 plus HVL times n hat 2. Okay, so that's the flux on the left side, so we can basically copy that and do it for the right side. So I'm going to cheat. So you saw chalkboard magic. Let's do some Vim magic. So let's just swap out L for R. And we're done. Nah, I don't need that. We know what it is. Typical scientist. All right, so we've got flux L, flux R. Now we need to calculate alpha. So alpha is going to be the max of what? We need UNL plus C, UNR plus C, right? And then we have UNL minus C, UNR minus C. So the maximum eigenvalue using either the left or right state, that's what we want to pull out as our alpha for the Lax-Friedrich solver. So let's clean this up. And I can already see a few errors I've made. Okay, so now we're looking pretty good. Now we just need to do some declarations, just a few. So we're going to change this to HL, HR. These guys can go away, so we'll say HVL, HUL, HUR. All right, so I think we've got just about everything we need. We just need those fluxes. So we need flux L, which is 1 to 3, and we need flux R, which is 1 to 3. Okay, so that's it on the Riemann solver on the CPU side. I'm not going to worry about the GPU stuff yet. Let's take a look and see if this compiles, resolve any of those errors, and then we'll walk through how to do the GPU components. We'll get those modified, make sure that builds, and then I'll dive into how the meshes are created and how those are brought in, and we'll write a little simple example program to do quiescent fluid with a flat bottom. So we're getting there, so hang tight. I am on my local system, so I've provided with Self a build system that I hope is portable. There's a few options. Last week I showed how to use the SPAC environment if you didn't want to use containers, or if you are on a system where you're not able to use Docker, things like that. Today I'm actually going to be using Docker with Google Cloud Build, in particular the Cloud Build local builder. And the way that works in Self, wow, I've got a whole bunch of output from before. Let me clear that. So the way this works in Self is underneath the Docker directory, there are images for AMD and NVIDIA hardware. And then there's what I call the base. Now the base image is something that provides basically all the dependencies you need to work with Self. So it's like HDF5, MPI, it's actually OpenMPI implementation, Flap, JSON, Fortran, and a few other libraries. Those take about a couple hours to build, so we've separated out the base packages into base, which if you were to take a look, we have one for NVIDIA and AMD. The main difference there is the NVIDIA one starts off of a CUDA toolkit Docker image, and the AMD one just starts from a bare bones Ubuntu, since all you really need is ROCm for the AMD systems. So the Docker file there, it's pretty lengthy, but it was generated using a SPAC's containerize method. So it installs all the things that SPAC needs. It installs compilers, installs SPAC, and then it uses SPAC to install all those dependencies. So HIPFort, HDF5, JSON Fortran, FEQ parse, and flap, which is used for command line interfaces. And then the actual Docker file is the bit that really all it does is install self, right? And it takes in arguments for the target architecture. So depending on if you want to run V100s, A100s, what have you, you'll set that target up there. Same thing on the AMD side. We have something similar. You'll set the GPU target as a build variable. Everything right now defaults on the AMD side to the AMD MI100s, and on the NVIDIA side to the V100 GPUs. So how the Docker files fit into the build process. Underneath the CI directory, there's a few different cloud build pipelines. There's one for pull request that's run if you were to submit code. It's what ends up getting run to make sure that what you're submitting is going to pass checks. It'll generate code coverage reports, all those bells and whistles. And in the next couple weeks, I'll be adding GPU benchmarking on Google Cloud as part of that to make sure that performance is staying consistent. The one we're going to be working with for local builds, and you can use on your own system, is this cloud build.local. And all this does is it runs through building that Docker image locally, and then it'll actually use that Docker image to run a handful of tests, which is essentially running the example programs that come with self. And it generates coverage reports. So this way, before you open a pull request, if you were to contribute stuff to self, you'll be able to at least make sure that 99% of the tests that I'm running, you can make sure you're passing them locally on your system before opening a PR. So that test script under the hood, essentially all it's going to do is run through a bunch of examples, make sure those examples run without failure, and then of course generate that coverage report. So if you wanted to build this way, the way it works is you need to install the gcloud SDK, you need to install Docker, and then you need to install Cloud Build Local. All this is documented in the self-read the docs, so you can get started with that. So yeah, let's go ahead and kick off that Cloud Build. So basically that command, what it does, right, we run Cloud Build Local, whoops, without scrolling up. We send it that config file, that cloudbuild.local.yaml. This flag is needed so that it actually does the actual execution, and then we'll give it the path, the root path for that build. The nice thing here, at least if you were to ever encounter bugs with your system, there's a very high probability that I'll be able to reproduce the problem you're seeing, so we can collaborate even if you're working on this from a distance on a completely different system. Just please, please, please do this on a Linux system. Scientific computing should be done on Linux, not Windows. I guess that's a personal preference. So if you hate that, definitely reach out in the comments. If you like it, reach out in the comments. So let's see what we get here. Make sure that we don't have any build errors. I did this last week and I did it again today. I forgot to add our new module into the build system. So we're going to need to do that. And in order to do that, we need to do a couple things. I'm going to go ahead and kill that for now. So we added a new module. So if I run the status, right, you see we've got two new files, the self shallow water and the shallowwater.cpp. We need to actually add that to the build system, and that's done in this make.include file. So if you come here, you're going to look for the F90 sources. Okay. And we're just going to add another model to that list. So you'll just put the prefix to, or just the name of the file without the dot, without the extension. And then we're going to need to do the same thing for the CPP sources so that those are resolved. And one thing we're going to want to do, because we changed the name from linear shallow water to shallow water in this module, let's go into that HIP module that we have and go ahead and just do that for now, even if they're not correct. We just want to make sure things compile. So let's search for linear shallow water, change it to shallow water. Now we should be good. So now it will actually grab self shallow water and .cpp, and it will grab self shallow water F90 for the build process. So let's go ahead and kick that off one more time. And while that's running, yeah, the beautiful thing with Cloud Build is you see these warnings up top. It'll do some cleanup, so you're not stacking up so many Docker images. If you were watching, I think it was like 3 or 4 episodes ago, I ran out of disk space by the end of one of these, just because I kept stacking up containers from various build processes. So Cloud Build Local certainly helps with that. But of course, after a development session, I'll go through and prune those containers and the associated images. I'm gonna go ahead and open up a new terminal, and let's dive in a little bit while that's building into what we're gonna do next here. So if you haven't programmed with HIPFort to do GPU acceleration, especially if you're a Fortran programmer, this might be a little weird. But Fortran 2003 started offering so language interoperability. So I can call C routines from Fortran, and C can call Fortran routines from the C side. And since essentially HIP depends on CUDA kernels, or what look like CUDA kernels, they're HIP kernels, they use the HIP syntax, which is almost identical. What you have to do is write those kernels in C++, and then you need to write a wrapper program around that ends up being exposed to Fortran so that you can call that wrapper program to launch the kernel. And that's done with this package called ISOC binding in Fortran. And then of course there's the HIP kernels themselves. So the beauty of starting with one of these pre-canned models that we already have and just building on top of that, is you'll actually see a lot of that infrastructure in place for you. So you can, again, just customize it for your specific solver. So at the top of the modules, you'll usually see these interface blocks where I have the name of the wrapper function that's defined in the C++ code with its variables, and then at the end of that line, we have this bind call, which comes from the ISOC binding class to bind it to a C function, right? That C is there stands for a C function. And then we have the name of the C function we want to bind to. And in Self, the convention is to keep the Fortran interface name the same as that C++ name so that there's no confusion about what we're doing. When you define these interface blocks, you got to add this ISOC binding layer. I also bring in self constant so you can get access to that that the C press type. Particularly, if you're changing between double and single precision, which we do allow for in Self, you can make sure those precisions are set correctly. Now the thing is, when you bring in ISOC binding, you also have the ability to work with C pointers in Fortran. And essentially that's how data is stored on the GPU in HIP is they're all C pointers, so they're all pointers to memory on the GPU side. And at the bottom end of Self, the very, very bottom end, it's all built on top of the Self memory class, which is essentially a definition for a whole bunch of like multi-dimensional arrays, one with host data, one with device data. The host data is a Fortran pointer. The device data is a C pointer. And I've provided methods out of the box to do, so for example, you skip through some of these. You can do basically host and device updates. So you can copy data between the CPU and GPU. And again, you can, from your perspective, it's just making a simple call like update device or update host. And underneath the hood, it's actually interfacing with HIPFort to do those copies for you. All right, so back to how this interface works. So on the Fortran side, what it looks like is an interface block so that I can actually make a call to this GPU wrapper. Now on the HIP side, if we go and look at shallowwater.cpp, turn on line numbering, and let's go up to the top here. So we got our set boundary conditions. So at the top here, so usually for every routine, you'll see 2 routines. You'll see one with the underscore GPU suffix, which is the actual HIP kernel. Now, if you've done GPU programming before, this looks familiar. For those of you who haven't, the way essentially you program HIP kernels and CUDA kernels is there's thousands of threads that are active on that GPU. And the API, the CUDA API and the HIP API provide a way for you to get what the what each thread's address is that launches this kernel or that runs this kernel. And the threads are grouped into blocks. Blocks are things that are groups of threads that operate in lockstep with each other. So you can think of them as a group of threads that are more or less in sync in terms of the steps in the execution they're doing. And then the blocks are placed into a grid, and threads in different blocks operate asynchronously. So you do need to be careful about race conditions and things like that. For the most part, if you look at the various patterns that are in self, depending on whether you're doing operations on element edges or if you're doing operations internal to the elements, I've got a lot of that worked out internally, so you can usually just duplicate what I've already done elsewhere. So for example, for the side, what I like to do is in the dimensions that vary the fastest, we'll use local thread IDs, and then indexing over like elements and indexing over variables and things like that, we'll use block IDs. So we're looking at doing things asynchronously. Because the nice thing with DG is if I go from element to element, the operations are really compact. So element 1 can do all of its operations independent of element 2. The only synchronization that happens is in those side exchange routines. So just keep that in mind. Now I have, so essentially what we need to do is think about, instead of putting do loops in here, getting those loop iteration values from the thread IDs and using that as our method for indexing through memory. So that's essentially what that exposes for us here. Now, in addition to that HIP kernel, we write this kernel. Again, it'll have the same root name, but the suffix will be GPU wrapper. It's enclosed inside of this extern-c method, or sorry, this extern-c specifier. And what that does, it tells the compiler not to mangle the name of that routine, so that when I do the binding to the C routine in Fortran, basically I can expect that the symbol name in the object file that's created is going to be set boundary condition shallow water GPU wrapper. If you don't have it around there, it's likely the compiler is going to mangle the name, and it'll start to include like the different variables for the API in that symbol name, and you'll get complaints from the Fortran compiler that it doesn't know the name of the routine. So we wrap it in extern-c, we create a wrapper, and all that wrapper does is use CUDA syntax to launch that kernel. So if you've never launched a kernel before, this is what it looks like. You'll essentially call that routine, and then inside of these chevrons, the carets, the left and right carets, is you'll provide what's called a dim3 object that tells you how many blocks we have in X, Y, and Z directions. So here we have 4 for 4 sides per element, and then NL for the number of elements. And then we don't use that third dimension in 2D. Now the dim3 for the size of each of those blocks, you can do also X, Y, and Z. Since on the sides we're just doing indexing over the polynomial or the quadrature points, we just need n+1. Okay, so you can see the same kind of pattern for like the source. So we have the source is an operation that takes place on the internals of each of the elements. So it's, again, the HIP kernel. It's got the global specifier up front, which I don't think I mentioned up top. That global specifier is used to indicate to the compiler that this kernel can be launched from either the CPU or the GPU. So yeah, that's that. So here, since we're in 2D, we use the local thread IDs for I and J, and then we use the block IDs to index over variables and elements. So very straightforward. We get very nice coalesced memory addressing. So we're at least taking advantage of the memory bandwidth on the GPU, which is kind of nice. So that's how that works. Basically, what I'm going to do between today and next week is go through and modify those routines to implement what we did on the CPU side. Let's go see how we did on the build. So far, it looks like we actually have some problems in self-shallow water, so let's take a look at what we got here. So C has no type, so let's fix that. And it is CL and CR, so let's go ahead and get that done. So Riemann Solver. All right, so at UNL, we need CL, CR, CR, and CL. Whoops, All right, let's see what else we got wrong here. Mismatch in argument H. Okay. So what I'm going to do is comment out these GPU kernels for now, the kernel calls for now, because that API is going to have to change, because we went from having the fluid thickness be a scalar to like a Fortran scalar, so a single value, to being a Fortran. Actually, it's a derived type at this point. So fix that. And I'm just going to go ahead and comment out these other ones because I think we'll run into the same problem for all these other kernel calls. So between now and next week, I'll be getting those updated. So if you keep an eye on our YouTube channel by subscribing, I'll be posting up some videos of some of the results that we get. I do have some linear shallow water videos that I'm finishing up, so those will be coming up soon. So keep an eye out for that. And then, of course, if you keep track of us on LinkedIn, on Reddit, whatnot, you'll see a lot of these updates come across, and of course on the GitHub repository for self. If you are interested in writing your own solver and you want to take a crack at it, these videos should be a good place to get started in terms of how this gets done. But of course, you can always reach out on the issue tracker. Let me know what you're thinking, and I can try to steer you in the right direction. All right, so I think that should do it. Let's go ahead and give it another build, and we'll see how we do. While that's going, I do want to talk to you about mesh generation. So what I've done recently is gotten rid of the inbuilt mesh generators. They didn't really scale very well when you did domain decomposition, and there's a lot of reasons for that, but essentially moved away to using, you can essentially use Gmesh or HOKmesh, which is an open source mesh. HOKmesh is an open source mesh generator specifically for spectral element methods. Definitely prefer using that for a lot of my work, especially in 2D. And then those meshes can get pre-processed through a tool called Hopper. And Hopper will reorder the elements along what are called space-filling curves. So when you do domain decomposition, it is more or less an ideal. It does, in some sense, try to minimize the amount of communications between MPI ranks. So I preferred to go that route where we just generate HOKmesh meshes or Gmesh meshes and pass them through Hopper, and then self is set up to read the output of Hopper for simulation. While this is here, before we hop into the mesh generation, I'll take a look at this. I've only got a few things left to do. Got an unclassifiable statement there. Looks like I misspelled flux at 372, so that's an easy one, and alpha has no type. So let's take care of those. So it's 372. Yep, there it is. Deluxe, that was not what it was supposed to be. And alpha has no type, so we need to declare that. All right. Got a rank mismatch in the velocity, and that's because I'm not indexing over the velocity there, so we'll get that fixed. So 341 and 344. Yeah, I totally botched that. So the variable indexes need to be 1, and the vector dimensions need to vary. Okay. What else? 344, 341, we got that. We got alpha, we got the deluxe problem. Let's take a look at 226. I'm not sure what's happening there. I'm missing a plus sign after the Coriolis force. Let's give that a go. Okay, while that's building, I'll go ahead and show you what the mesh. So I've started to include a few of the meshes that we use for testing. So you got a block 2D, block 3D for when I start putting in the 3D stuff, and I'll show you circle because that's by far the most interesting one I've got in here so far. So I also have, I've made a fork of Hopper so I could add a Docker file to it and create Docker images, so it's a little bit easier to do the post-processing like in a pipeline. Or sorry, the pre-processing in a pipeline. So I'll pretty soon I'll be putting up some documentation on how to get access to that. And then we've got HokeMesh, which if you remember from last week, we can install HokeMesh pretty easily with SPAC. I'll also be putting HokeMesh into Docker containers, so we'll get those images out there soon. The way HokeMesh works is you can write these control files that look a little bit like LaTeX syntax. And there's usually a few sections, so you have what's called the control input that kind of dictates things like where you want your file I/O to go, polynomial order, stuff like that. When you're using Hopper to process HokeMesh files, you'll use the ISM format. We'll set a background grid size. Maybe I'll do a live stream in the future here to talk a little bit about the methods here behind HokeMesh, as I've gleaned from the author of that library. It's pretty fascinating how those meshes get generated. But essentially, the gist of it is you'll start with a square mesh of a particular size, and then it tries to adjust the boundaries to fit onto the physical boundaries that you define, and then it kind of shifts elements around, adds and subtracts elements, so you get good mesh quality. What we want to do in the model for the circle is essentially just define a circle of radius 1. That's really it. When you process this file with HokeMesh, so I'll just run through an example of how to do that. So I've actually got it installed on my system already. You can just pass in that control file through standard in, and it generates, what it actually generates for you is a few things. So we get the ISM file, which is this mesh file. We get a tech plot file so we can visualize it. And normally there's a debug output, but I think I might have turned that off for this one. So let's pull that open in ParaView so you see what that looks like. Okay. So in ParaView, we'll just go ahead and open up that tech plot file, which the tech plot file is included in the repo if you wanted to take a poke at that. Let's just put on solid color and put on the surface with edges. So you could see those element boundaries really by where those like thicker lines are, because that's where those edges are going to overlap between neighboring elements. And then these lighter colored lines that are unevenly spaced are those quadrature points I was mentioning before. So now what we do is, if I don't think I have, I don't have the element IDs with this particular mesh. So I couldn't show you the element ordering, but it's usually not great for doing domain decomposition, and that's what Hopper's primarily used for. That, and it actually makes it easy to use Hopper, so I can take in multiple mesh files with Hopper and then just convert them to one format that self can read. So when you go to run Hopper, and I'll actually just do a run with Hopper inside of a container with a bind mount to the current directory. So if I go into workspace, I've got all my stuff there. So I'm going to do Hopper. So Hopper takes in another file. It's another parameter file. I've called them parameter.ini. I put the links to the documentation for the parameters up there because there's quite a bit you can work with. But for the most part, if you use any of these as templates to start, it should give you a good jumping off point. But essentially what we need to do is tell it to use mode 6, which is the SpecMesh 2D reader. If you're doing like multi-zonal meshes, things like that, you can actually have that built in there, but there's some other stuff you got to do in HokeMesh, so don't worry about that. We'll give it the file name we want to process. Now Hopper is really a 3D mesh tool. So what it's going to do is do an extrusion of the 2D mesh we send it from HokeMesh. And so in order to read in a 3D mesh from Hopper in Self, what I've done a little bit of a hack where it's just going to read the bottom layer of that extrusion. And the easiest way to guarantee that I can grab that inside of Self is just set that Z length to 1, the number of Z elements to 1, and then you can do whatever you want for the boundaries, but make sure that VV, so the extrusion direction, is in the Z direction. Outside of that, if in HokeMesh, which I'll be covering in the next few tutorials, how to do different boundary conditions, you can set essentially right here in this first, so this is the boundary type. I think it's the second or the third one. Don't quote me on this, but one of these is actually going to be used for your boundary condition flag. So it'll look for the word outer in the boundary condition specification side of the hook mesh and replace it with an integer boundary condition type. So you can do no normal flow or radiation. All right, so Hopper is going to take that parameter.ini and oh, I'm not in the container. So here we go. Now I'm in the container, and it's going to process that. And it wrote an HDF5 file. This is the one that goes into self, but we also got for free some VTK output, so you can look at some more information. So let's pull up those debug meshes. So you got this is the debug mesh for boundary conditions. So if you wanted to check all the boundary condition flags, you'll have that. And then we've got the actual spline surface. So there's a lot to talk about there, why they're doing it this way, but that might be for another day. So let's take a look at the debug mesh. I'm going to turn off this one. So this one is actually in 3D, like I said. So you actually get a whole 3D object. It took our circle and it extruded it. So if I do surface with edges, so we still have our the element boundaries are still the same. It just extruded it into 3 dimensions. And again, like I said, my hack in self is just to take that bottom face off of this thing. So this is the debug mesh. We can look at like element IDs, so you can see the ordering, and you can start to see if even with this color map, not the most ideal, you start to see blue elements that are placed next to each other, lighter elements placed next to each other, and red elements together. So that if I were to do a domain decomposition just by taking an array of 1 to n element and just evenly divide it, I get an easy way to do my domain decomposition. Now, if you wanted to actually see the full curved object, this is where you'll want to pull in that spline volume mesh. So apply that guide. So now you actually see like what's really held in there for that geometry that what we use for the discretization actually does have curved sides to it. So if I put those surface with edges in there, you can see all the grid points we actually have. So when you read it into self, you should feel confident that you actually are getting curved geometries. So that's pretty much how this works. If you wanted to look at other things like the element Jacobians from the coordinate transformations, you can see how that lays out. This is kind of knowing what the Jacobian values ranges are and whether or not those elements are they're I guess symmetric in each direction. You can start to infer like what your time step size needs to be, things like that. But so that's pretty much how the mesh generation works. Is you'll use an external mesh generator like Gmesh or HokeMesh. You'll run it through Hopper, and you can drop those in. If you're building tests and new models, you'll usually drop them in this etc mesh directory so that they're available in the code. All right, let's see how we did. Looks like we actually compiled, and you can see the coverage report is there. So we're looking good. I think we're ready to go ahead and develop our example program. So we'll take a crack at that. So if you want to, when you're ready to add an example program for a solver, you can go into the examples directory and take any of the existing examples that are there. I usually like to start very simple. The block meshes are a very easy way to start to make sure things are working. And I'm assuming, Ronald, this is a comment on the fact that I'm using Vim. Yeah, that's my IDE. People have called me a geezer geek, but I'm nowhere near being old, so I'm glad you find that surprising. So what I like to do is start with a mesh that doesn't have complicated geometry, so it shouldn't have like isoparametric elements that are curved. Usually starting with something with straight sides is a good place to start to make sure that like some of the basic stuff's working. And in this case, this is why we're starting with a quiescent fluid. If I put in a flat bottom topography, I should be able to get no motion, essentially. So let's go ahead and talk about how to write the main program, and we'll go from there. So I'm going to go ahead and take the linear shallow water gravity wave release program, block mesh, and we're going to just do, let's copy that and modify it. All right, so we got shallow water is the model that we're doing. This is going to be, we'll call it quiet fluid on the block mesh. All right, so let's go ahead and open that guy. So this should give you an idea, like the reason why the self structure is the way it is to make writing programs to simulate various processes a lot easier, and it makes it very flexible so you don't just have one monolithic static code to work with. This is starting to get in a workflow that's more akin to what people are doing in Python notebooks and Julia, and I'm really looking forward to what the Fortran group is doing, which is essentially a notebook style compiler or just-in-time compiler for Fortran, so we can do things like this in a more of a notebook fashion. Anyways, that being said, what we need to do, what you'll usually want to have in your main program is you know, the Lagrange class for your interpolants. You'll want the mesh class, the mesh module for all the mesh types, geometry for handling isoparametric geometry, and then of course that module for our model that we just wrote. And the way this works is we're going to essentially define the interpolant that we want to use. We're going to define a mesh, and then we're going to define the geometry. And once we have these things, we're going to initialize a domain decomposition. I'm not going to get into using MPI quite yet, as it's a little bit more advanced. But in the future, you'll see how that gets used in practice. But regardless, even if you're not running with MPI, you do need to have a decomp set in order to work with self. So usually what we'll do is we'll initialize the decomp, set the MPI to false. That's good enough. So we'll create our interpolant. The interpolant initialization, essentially you need to provide it the polynomial degree you want to use for your mesh. So I've defined that up in the parameters up top to 7. And the reason why I use 7 is because on the GPU, this is going to give us 8x8 operations, which maps very neatly onto a single warp, or 2 warps on an NVIDIA GPU and one wave front on the AMD GPUs. We're going to give it the quadrature type. When you use the Gauss keyword, this is the Legendre Gauss. It's definitely what I prefer to use. And you can also use Gauss-Lobato or Chebyshev-Gauss, Chebyshev-Gauss-Lobato. And then the other 2 arguments are what are called the target quadrature points, because an interpolant in Self's world is always going from one grid to another. And usually what I use the target grid for is for doing tech plot output. So you can use the uniform quadrature for your target, and then you'll set that to how many uniform points you want per element. So here I've got it at 15, which again gives us another multiple of 64. So it'll be 16 by 16 because we start at zero-based indexing for the quadrature points. So here's where we actually read in the mesh. So you can, in Fortran, get an environment variable. And for the example programs in the Docker files, we define self prefix to be the directory where self is installed. So if you want to use in the Docker container in the build system, use any of the meshes that are provided in that etc directory, you can get that full path pretty easily just by getting the self prefix environment variable, pulling that in, and then referencing etc mesh, and then pick your mesh from there. And again, it should be one of those hopper files that come out the other side. It's called read hopper. Usually we call the generate decomposition, which if MPI is set to false, what this will do is just say, hey, serial process, you're doing everything. It'll assign all the elements to that serial process. So that's pretty straightforward. This can actually go away. Then we initialize the geometry. So the deal in self is everything, the solution, the geometry, the flux terms, everything has the same interpolant. So we're going to pass that interpolant through to initialize the geometry to use that. And then we can generate the metric terms from the mesh information that was read in the hopper read. So this is a fairly typical structure you'll want to repeat if you're creating a program. You can just grab one of these example programs as a template and off you go. And then you can, from there, once you have the interpolant mesh geometry decomposition defined, you can create your model. Once you have your model, we can do other things. So if you turn on GPU acceleration with this API call for the model class, essentially it will try to look for a GPU first. If you have one, it will set a flag internally to default to using the GPU kernels rather than the CPU kernels. And when it does file I/O, it'll take care of handling mapping data back from the GPU before doing that file I/O. Now for the initial conditions that we're going to do here, we're going to actually set the total fluid thickness to the background velocity. So we're going to actually need to define a few things. I'm going to keep it easy. Just set these to 0. So this is where FEQ parse comes in. So FEQ parse is another library I wrote to essentially interpret strings and do function evaluation in Fortran. So we can just basically provide these strings, call this set solution method, which underneath the hood calls FEQ parse to set the initial conditions for the solution. So I'm already seeing one thing we need to do is we need to have a SetTopography class, SetTopography method, so that we can get that in there. This also reminds me I didn't define that PreTendency method, so we'll do that here in a second. We'll write out the initial conditions. So you can set the time integrator now in self. Right now I shouldn't have this RK4 here because I'm still working on that. We can do RK3 for rung ahead of third order. You'll set your time step, and then you can forward step the model. You can specify the end time that you want and how frequently you want to dump out that model output. And at the very end, we'll write a pickup file. So later you can actually do a SEM model read model if you want to start from an initial condition that's already provided. And then you got your cleanup. So that's basically it there. Let me go ahead and so this is quiet fluid. Not quite fluid. Shallow water, quiet fluid. All right. So that's the gist of the main program. Now the other thing you'll want to do, just like we added the module to the make system, we need to go back into make include and add shallow water, quiet fluid, block mesh 2D. So let's go ahead and do that. You're going to go to the examples this time, and you'll add it to the examples. And basically, as long as you put if you're contributing a new example or if you're contributing a new model and you add an example, as long as you do it this way, it will automatically be added to the suite of testing and be included as part of those coverage reports. So trying to make this a very methodical process to make it easy for a lot more of us to get involved in building out these kinds of tools. That's the gist there. We do need to take care of two things. So we need to set topography, and we need to set the velocity in the PreTendency field, or in the PreTendency module. So let's go back into the source. Let's take a look at self-model, and let's look up PreTendency, because essentially we're going to need to preserve the API for PreTendency, but override it for the shallow water system. So we've got 327 down to 340. That'll give us 13 lines. And let's go ahead and pull up shallow water. We're going to do a procedure override for PreTendency, and we're going to call it PreTendency shallow water. So in this section, when you declare inside the type, what we're essentially doing is making a type bound procedure. And in this case, we're going to override this PreTendency routine that's included in self methods, or the self model. The reason why we want to override that one is because in the calculate tendency routine, you can take advantage of a pipeline or a workflow for advancing the model without having to make a lot of adjustments. You can simply just replace what that PreTendency method does. So this is the nice thing about some of the OO features of Fortran that I've really been enjoying. So let's go ahead and define this guy. Let's go underneath the init, I suppose. So PreTendency, what do we want to do in PreTendency? We want to calculate the velocity at the interior, at element interiors, and element boundaries. So we'll have two things to do there. And instead of having the suffix of model, we're going to change that to shallow water. Okay. Whoops, did not apply it. All right, so that's that. And then we need two loop structures, because if we're doing the interior and we're doing the boundaries, and again, this is another little bit of a nuance. I don't know. I haven't really thought about what's the correct way to do this, but essentially we can loop over the interior elements and compute the velocity, and then and do a boundary interp to get it over to the boundaries, or I can loop over the interior elements, calculate the interior velocities, then loop over the element boundaries and calculate those directly. I haven't thought about which approach is most appropriate. I'm going to do the easiest thing and take advantage of the boundary interp inside, and I might do some work in between on the theory side to see what that might suggest is the correct way to go about it in terms of like numerical stability, etc. So actually I just need one loop structure here. I need an interior loop structure, so I'm going to steal that from the source method. So I got these two lines I'm going to take, and we'll drop that, and then we'll go ahead and declare those loop variables. All right, so now I've got, instead of source, let's do solution. Whoops. Okay, and then what we're gonna do is we wanna calculate velocity, so that's this velocity. We want interior. We want the host data, we want ij. We want the first one. ij1il is gonna be equal to, so we're going to get HU divided by the fluid thickness. So this will be, so let's go ahead and just do this. We'll do H is this percent solution, percent interior. We want the element interior, host data, IJ3 for the fluid thickness. And then we'll do HU, which is the first one, IJ1IL divided by H. And then we'll go ahead and grab the second one here. Whoops. So now we got the second velocity component is HV divided by H. Okay. And then what we can do, for now, since I'm not setting this up to run on the GPU yet, I'll be doing this again between this week and the next 2 weeks. We'll do is this percent velocity. You can take advantage, I need to spell that right. We can do boundary interp and then set the GPU acceleration explicitly to false. That's it. So basically what we did up here was calculate HU divided by H. We did HV divided by H here to get the velocities. And we just did the boundary, we called the boundary interp method to get that on the boundaries as well. Because we're going to need that for the Riemann solver. The interior one's needed for the interior flux calculation. Is there anything else? I think we're good there. We do need a SetTopography method. So let's go ahead and do that. And if you want a good example to build from, we can borrow from the SetSolution method. So the SetSolution has a couple interfaces that you can use. You can either send in an FEQ parse equation, or you can send in the character. We're just going to go ahead and steal both of those and just override them. Well, we're not going to override. We're going to use them as templates for our setup. So we'll go ahead and take these declarations. Let's go back into shallow water. Let's add those procedures. I'm going to put this as new methods, just so we know. So we've got a solution we want to change to topography. Okay, cool. So what do we need to do for topography? Well, first let's go ahead and grab these guys so we have the templates to work with. And 1394 down to, oh, that one's, okay, so we'll copy this one and then we'll get the one from equation next. So 1394, set 6 and 13, so that's going to give us 19 lines. And, you know, since this one's really not going to be called over and over, it's basically something that gets called at the very beginning of the program, we'll just only do this one on the CPU, and then we'll take care of just migrating data to the GPU side. So let's set model 2D to shallow water. And then let's go grab the from equation version of this. Here we go. That's velocity. Here we go. Set solution from equation. So 27 down to 47. That's a nice even 20 lines. All right. And let's do that find and replace again. Okay, so this time what we want to do, so in this template, what it's doing, right, is it's setting the solution. And actually, for the topography, we don't have multiple variables, so we don't need an array for the equation character. Oh, right, let's go ahead and just change that solution to topography. Great, before I forget. All right, so we don't have multiple variables for topography, which is nice, so I don't need that loop. And we're going to change all these solutions to, whoops, all these solutions to H. Whoops. Let's try that again. Ah, my capital S. There we go. Now, the other thing we need when we set the topography is the gradient, right? And the way we're going to calculate the gradient is using, so the H variable is the mapped scalar 2D type. So if you were to go into the map data module and look up scalar 2D, okay, so you've got a map scalar 2D, there's actually a gradient routine associated with that. So you can just use that to calculate the gradient. So that's what we're going to do. So let's take a look at that API so you know how that works. Okay. It's not a, no. Why do we need a work tensor? Don't think that's not needed. This is, oh, I suppose it is. Okay, I need to actually fix this, as this is I thought this was an older version of that method, but essentially what we're going to end up doing, I need to get that cleaned up so we can do that. But what we'll do is we'll call this %H gradient. I think I have this on another branch, so I'll get that fixed. Is you'll just send in the geometry, and then what we get out as output is the gradient, which is grad H, and then the D form we want is the strong form. So let's see what the field is for that. So that's self weak DG. We want self strong form. Okay. Whoops. There we go. And the GPU acceleration we're gonna explicitly set to false. Okay, so once I get that cleaned up, that'll be fine. I'm gonna comment it out for now because I need to fix that API. But that's what that will look like, and then we'll just basically do the same thing down below for when we set it from an EQ parse. An FEQ parse, an equation parser object. So the only difference here is we don't need to create the equation parser, we just get to copy it, which is sweet. So we'll do that, and then let's go ahead and bring back in that gradient call. And in between this episode and the next, I'll get that API fixed for the gradient calculation. Okay, so we've got that, and we can roughly assume that we'll have the bottom topography gradients. I probably won't get to the example where we have the varying bottom topography, but I'll at least do the quiescent fluid. So we do have a way to set the topography. So let's go back into our example program and add that call. So here we go, SEM model. We're gonna do, so we got the initial condition. Let's go ahead and set the topography. And I'll just do it with a character. We'll just say H equals 1. And the variables on the left-hand side really don't matter in this. The only thing that you need to keep in mind is FEQ parse expects all the variables right now to be just a single character. So if I were to do like HV, that would not be interpreted correctly. I'm actually not sure what it would do, so just keep that in mind. So we'll set the topography, we'll set the initial condition, and then we're off and running. For now, I'm going to make this I'm going to do it just a single time step. So we'll set the final time to a millisecond, and then we'll set the I/O interval to a millisecond, just so when we test, we can just do something really short, make sure we get no tendency, and off we go. So yes, we are committing a crime here in the fact that we're not actually putting in the topography gradient, but for this specific test case, the gradient in bottom topography should be 0 anyways. So we'll take advantage of that. Okay, let's give this a compile, and then I'll show you how to run this code and visualize it in ParaView. I suppose I could show you how to visit, but just for another day. Yeah, then basically from here I'll be up and running with another model for us to test out, get ported to the GPU, and start sharing some results with you here in the next couple weeks. Let's go ahead and exit out of this Hopper container. Okay, so I got a few errors. Okay, we'll take a look at what we did wrong here. IVAR has no type. Okay, so because that method does expect the number of variables to come across, so we'll just hard set that to 1. We need to change model 2D to shallow water up there, so let's go ahead and do that. Shallow water, let's go find model 2D. Here we are. That should take care of that issue. What are the other ones? H has no implicit type. So at 167. Oh yeah, I remember that. That was my bad. So we just need a real Fortran scaler to handle that. What else? 214, we got no specific, oh, and that's because the IVAR was not defined. That caused that error. Okay, so let's go ahead and just do this. Because the set equation method does expect a variable ID for doing this, so you can set individual variables by a character string or an equation. Actually, it's an FEQ parse equation. We do need to put something in there. IVAR wasn't defined above, and that would definitely cause an error because IVAR was not initialized. So although it would probably compile, definitely would cause some problems running. EQN char is not an array, so we can get rid of that. And same thing here, we can take care of that. Okay, fingers crossed that we got it this time. Let's see how we did. So, all right, I'll leave that alone. We'll need to get ParaView back up because I'll start creating some output, and I'll show you how to visualize the output from self. And you know what, while we're in there, I'll actually show you what happens with the linear shallow water solver, since that's also an example. So that was actually pretty exciting to see that get done. So a lot of warnings, so I'll get those cleaned up for unused variables. No big deal. But it looks like we were able to compile. So let's just make sure our program compiles and runs now that it's integrated into the tests. And once this is done, I'll show you how in your local environment, if you're building in this method using Docker and Cloud Build, how you can use that container, the container image that's created from this build process, to go in and manually run things so you can get model output to experiment with. Of course, the other option too is if you're a Singularity user, you can always Singularity pull from the local Docker daemon and run in Singularity if you're on a system that doesn't allow you to do root escalation. SetTopography is not a member of the, oh, I have one too many O's in that example file, so let's fix that. You know, that's what I've learned is the majority of programming mistakes are simple typos that if you're not getting enough sleep or taking care of yourself mentally, you'll very quickly overlook them. So I suppose the life advice, if you were to take it from me, would be make sure you're sleeping well and taking care of yourself, because it can just make the rest of your life so much harder. Little things like that. I've had some sleepless days of programming nonstop where I would never have seen those two O's there, and it would have driven me mad. So I'm sure some of you out there can relate. All right, let's see where we're at. So yeah, definitely relative to building with SPAC, this can take longer simply because Docker is going to restart the builds from scratch in self. So even if I compile the entire library and I get to the end and it's just the program that failed building, it's going to rebuild everything from scratch. Whereas like when you're building on close to like bare metal using a SPAC environment, it's going to take it, the make system's going to take advantage of the fact that the rest of the library compiled fine. So I guess there's one drawback to building this way, but the reproducibility in the environment is really a big win, especially when it comes to trying to collaborate with others who might be on different platforms, different operating systems, have different environments altogether. The SPAC environment does do something to try to address what packages are available, but it's certainly not perfect. So let's see how we do. Looks like it's getting through tests here. I see linear shallow water everywhere. Looks like it's running another linear shallow water right now. Let's hope in a second it gets to the one we want to see. But this is a good sign that we're actually running all of our examples. So. Once we're done here, we'll hop into this Docker container, run the model, produce the output. We'll open it up in ParaView, take a look at it. Because the other thing I like to do in these examples is compare the output with an expected value, especially in these situations where you know what the exact solution's supposed to be, so that we can throw non-zero exit codes if the solution is not that. So it definitely helps with the, as you're building examples, visualizing it is great, just to make sure you're in the ballpark area. But if you're constructing an example where an analytical solution is known, that's like the holy grail of testing here for self. Because the other thing we're going to start doing is running convergence tests to make sure we're getting spectral accuracy and that H refinement as well. So when you reduce the element sizes, it gets the correct convergence rate. So all these things are coming, but it's always incremental, just so we can kind of keep pushing forward one footstep at a time. So far we're looking good. This is looking great. Yeah, it looks like everything ran. Now the question is, did we get the right answer? Since I didn't put in a check in that program, we're gonna have to hop in. So let's run in here. So essentially when you run Docker, we'll use a bind mount to mount the current directory into the container at a place called workspace. Sorry, this is getting cut off on the screen. But when I get out of here, I'll pull that command up again. So if I go into workspace, I'll have basically what I was seeing on my local system. So we'll go to opt self where it's installed. We've got all our example code, so we can run shallow water quiet fluid. And it ran, and now we've got some tech plot output to take a poke at. So let's go ahead and open up ParaView again and take a look at that. Make sure we're doing okay. So one, we'll verify the mesh got read in. Go up a couple directories. Here we go. Solution.tech. So you can see in the data arrays, we've got H, HU, and HV, so we can go ahead and apply that. Let's take a look at just solid color and make sure the mesh looks good. So we got surface with edges. So it did reinterpolate to uniform mesh, so hooray. Let's just go back to surface and let's turn on H. And the H value, on the bottom end is blue, so it's set to 1. So that looks okay. Let's take a look at HU and HV, which should be 0, and indeed they are. Okay, and then let's take a look at the next time step. Whoops. So let's put H back on there. Let's take a look at that next time step. And we've got some garbage. So what I'm going to do here is make sure that the boundary conditions are set to radiation. And there's a method we can use for that. So go ahead and hop out of that container. And just for clarity, that docker run command, so you'll do docker run -it, which so we can basically drop into a shell. The entry point here is basically a shell that loads up the SPAC environment inside the container. We'll do a bind mount, and then we run the self container that we built, which here was built for double precision for a V100, which you can use that to run on a system without a GPU. That's fine. So in the examples, the one thing we want to make sure is we didn't accidentally set the boundary condition to something we didn't want to do. And I'm going to force it. Let me figure out which one I did this in. I think it's in the reflecting one. There's a method you can use to reset the boundary condition. So here we go. For the mesh. So we'll put that in the quiet fluid setup, and this way we can be certain the boundary condition flags are set to what we want them to be. So after we create the mesh, we'll create the decomp. Let's go ahead and do it right after we do that. So this is no normal flow. We'll experiment with this here in a minute. So we're going to set this to radiation. If you're curious where those are defined, in the source class in self model at the very top, we got boundary condition parameters. So those are the ones that are currently defined. I'll be putting these in tables and getting those up in the read the docs, but that's where they are. Okay, so we're going to make sure we got the boundary conditions set right, because obviously that caused some problems, what we currently had. And if we are certain we're using radiation boundary conditions and that's not correct, what I'll be doing next is kind of revisiting how those are defined in the code. Actually, let's just double check real quick, because I just had a sneaking suspicion about what's wrong. So we pull in H boundary host data. In theory, if I came in and hard-coded this to 1, this should be fine, but all right, well, I do the boundary interpolation anyway, so yeah, this should still be okay. So let's hope that that's the case. And of course, the other thing too is the Riemann Solver, making sure we have that correct, since it seems to be something coming near the borders of our system. So let's go ahead and rerun our build. Actually, to speed that up, I'm going to go ahead and comment out a few of these so we don't have so many running, just for now. Okay. So we'll do that. We'll build that. Let's take a look back in ParaView. Yeah, so what I'm thinking is going on here, so let's rescale this, is there's definitely an inconsistency at the boundaries. This is like, if you look at the color bar here, the red is now 1, and the blue values and anything lighter in color is going to be less than 1. And what it seems to be happening is at the boundaries, we're getting very, very small values that are being projected onto different polynomials inside of each element. And that will basically generate spurious gravity waves that will, if I were to keep running this, propagate to the interior and probably crash the code, because it'll keep generating this garbage. So try to figure out the root cause of that. These are always the most fun problems, because like the code compiles, the code runs, but it certainly is giving an incorrect result. So we'll see what's going on there. Take a look at this build. All right, that was much faster. That's good. Let's regenerate that output. So we'll go back into that container. And if I can't deduce what's going on here, or if this hard setting those boundary conditions didn't solve the issue, I'll probably stop here, and then we'll pick up. I'll post some solutions in the next couple weeks. But let's go back into that workspace directory, opt self examples, and then here we're going to do shallow water, quiet fluid, to make sure we got new files, and indeed we did. So there's our solution 01.txt. Let's go in pair view, reopen that. Okay, so it definitely is a problem with, so we got the same answer, and we're certain it's the radiation boundary conditions. So I'll need to revisit those radiation boundary conditions and make sure we're good there. I'll need to check the boundary state for the fluid thickness to make sure that's okay. Because if that's not being set correctly, that could definitely be part of the problem. The other thing that could be happening is, let's go take a look down at that Riemann solver. So let's take one more look at that Riemann solver just to make sure. But if this is looking bad, then I will, oops, stop here. Okay, so all right, so Riemann solver, HUH. HV, HL, those look fine. Oh, I think I know what the problem is. Maybe I need to actually do a side exchange for that velocity, but I didn't do that in the PreTendency. So what we need, what I'm thinking is calculate tendency. Let's go in there. So in the calculate tendency method, what we got, right, is the solution. We do a side exchange for the solution. But we haven't done that for the velocity field. And so when I pull the ext boundary for the velocity field, I don't get anything meaningful in that field. So that could be populated with garbage and could be impacting the Riemann solver. Either way, if that's not the cause of this specific problem, it's certainly something we need to correct. So let's go in that PreTendency, and we're going to add that step to the PreTendency calculation. So we calculate the velocity, we interpolate it to the boundaries, and then we need to do a side exchange. And again, this is done even if you don't have MPI. It is something that's needed to populate that ext boundary field. It just so happens that if MPI is enabled, what it's going to do is, if MPI is enabled, it's going to do the MPI I send and I receive underneath the hood for you. So we're going to give this a shot. If this doesn't work, we'll call it for the night, but fingers crossed that this solves the problem here. So let's go ahead and rebuild that container. I suspect that could be part of the issue, because if I have garbage values for that external velocity field, that would be certainly contaminating. I guess that would actually contaminate more than just the boundary, so maybe that's not it. But either way, it needed to be fixed. We'll take a look, and otherwise, well, we'll see what happens here in a couple weeks. So we're doing okay so far. So the cool thing about this build system too, right, is if those build pipelines work locally, of course, when they go up to the repository, we're basically running the same steps in these other CI builds. So if you guys are thinking about building out your own solvers and contributing them yourself, I'm trying to make this as easy to use as possible. So if you get your hands in there and you have any feedback for me, definitely let me know. All right, so that's running. Let's go ahead and get back into that container. Let's try one more time. Okay, so we'll do opt self examples, shallow water, quiet fluid. Make sure we got new files, and indeed we did. So let's go back in pair view, reload, and we still got the same garbage answer. Okay, so I'll need to take some time to figure this one out. I do appreciate you guys joining again. If you want to keep track of what we got going on, I do these every 2 weeks. Subscribe to the Fluid Numerics channel down below. If you like this video, definitely hit that like button. And in 2 weeks, what we're going to be doing, of course, is I'll have these things resolved. Tell you what, while I got you here, I'm going to do one more build. I'll show you the linear solver. So let me go get one of those added back in here so you can see what those turned out to be. Let's say we do, I don't know. Let's just do the block mesh with the radiation boundary conditions so you can at least see something cool come out of this at the end of the day. So I'll go ahead and rebuild that. But yeah, if you like what I've got going on here, definitely check us out. We have you can find us on Reddit, rFluid Numerics. Of course, you can follow me on LinkedIn or Fluid Numerics on LinkedIn to keep track of what we got going on. Once this is done here, we'll do a nice little simulation of a gravity wave going through this through a square domain, and we'll call it a day. So seems like the industrial area of Boulder is hopping tonight, so I don't know if you guys can hear that in the background. All right, almost there. Go ahead and kill this because we're going to overwrite those and load in new files. Looks like we're running tests now. There we go. So let's go ahead and hop back in that container. And oops, no, I wanted to go into workspace, so I'm in the home directory. Let's go ahead and remove those solution files. Self examples, and then we're going to do our linear shallow water gravity wave release. So that's running and takes a few minutes. We've got a whole bunch of output, so let's go ahead and open that up in ParaView. So go ahead and apply that, and to make things a little bit pretty, so there's our free surface height as a 2D object. Let's go ahead and add a filter, warp by scalar. So this will make the free surface height bumpy. So let's change it to 3D, and now I can do something with that. Let's change that scale. There we go. And let's make this just a, let's do surface with edges, and coloring, let's do a solid color. Why not? Make that prettier. All right, cool. So there's our initial condition. We just got a little bump there in the center, and essentially when this goes off, you know, it's going to generate flow, and that gravity wave is going to exit out those boundaries. So this is from the linear solver we got working from last week. I thought I had it working. Something changed. Things got bumped around. What's going on, ParaView? Wow, that's embarrassing. Tell you what, I'll show you the video that I generated because I don't know what the heck happened there. I think I based off of the wrong version of self when I started today, so shame on me. Let me pull this up for you because we did get something going. Let's see. Here we are. So we got a suite of these that we did. So here's our square domain that we were able to get running. I'll figure out what's going on here in just a minute. Here's one with the reflecting boundary conditions. It kicks waves back into the interior. And then the circular domain that we showed earlier. So do try to keep these things interesting. Thanks again, everyone, for tuning in. I'll catch you in 2 weeks. We'll be talking about how to do split form methods to stabilize the nonlinear solver, which of course we'll get working before the next series. I hope you found this useful both for learning about spectral element theory and programming GPUs in Fortran. So I'll see you guys in 2 weeks.